So we want to approximate our stabilization parameter, for which we now found an explicit definition based on these fine-scale Green's functions as an element average of the integral of that fine-scale Green's function. Now, we said this was not very practical because these expressions for the fine-scale Green's functions can be very complex, and we've made so many approximations at this point that it really doesn't make sense to use a definition like this in the multi-D case. What we're going to do is we're going to go one layer deeper into our approximation, which again we make consistent with the one-dimensional case, but at least get something out of there that is usable and very practical, and we can implement also in multi-D. And the way that we're going to do this is that we're going to look at the limiting values for tau. The limiting values in the sense of pure diffusion and pure advection. And then we'll try to combine those limits and obtain an expression that reverts to those limits in the limiting cases. Okay, so we're going to take the limiting values and we obtain these limits in the one-dimensional case. So I'll define those as tau A and tau D for tau advection and tau diffusion. So it means that tau A is the value that we would obtain if k is equal to 0. So what does our partial differential equation look like then? Well, it's going to be minus, because again we're dealing with the adjoint differential operator, times A times D dx acting on some field phi, and that had to be equal to our Dirac delta distribution at some point x hat. So now it might look like I'm asking something near impossible. How do we solve something like this? Well, it actually ends up being quite simple. I can draw this already. So here I have a mesh of elements. And well, first of all, remember that we have this element localization. So my fine-scale Green's function is going to localize to one element. And secondly, if we look at one of these slices, you can already kind of imagine what this is going to look like when the diffusion gets lower and lower and lower. It is this, the effect of the diffusion is this smoothing out here, and here. So if I reduce my diffusion further and further, this is going to smooth out more aggressively or less aggressively and less aggressively. And in the limiting case, I actually get a step function. So the limit case is going to be a step function at when my x hat is right here in this element. So how high is that step function? What is the y value of this guy? Well, let's take a look at our definition here. We have that minus a times d dx of phi is equal to delta. Well, we know that the derivative of a step function is indeed this delta. Now I have a step function that goes down, right? But I have a minus here, so that's fine. But the derivative of a unit step function is equal to the Dirac delta distribution, right? So if we take 0, 1, and I take the derivative, then we obtain, this is the derivative, right? Then we obtain the Dirac delta at this location. So we somehow need to normalize with respect to a, so that means that the height of this guy is going to be 1 divided by a. Yeah, so if I take this function and I substitute that in place of phi, so maybe I should simply be saying g here. Yeah, sorry, that's what I should be saying. Then we find that this is going to be equal to the delta x hat. Okay, so now all I need to do is plug in this Green's function into my definition of our stability parameter, which was, well, 1 over the magnitude of the element, well, that's going to be h, of the integral over the element, so that's going to be 0 to h, of the integral over the element, again, 0 to h, of our Green's function, g, x, comma, x hat. Yeah, okay, so I'm writing here y. If I want to be consistent with my y, then I I have to say y here, but then I would also have to say y here, and then it's also going to be ddy. And then I think we're good. So I don't like that. I'm going to say ddx here. Then, well, it's just a change of notation to change this back into this this form here. So it's going to be an integral over dy and dx hat. Now that looks like a complex expression, but it tends to be, again, it turns out to be quite simple. Because that inner integral from 0 to h of this Green's function, well, that's actually not going to be anything other than from 0 to x hat. So we actually get 0 to x hat, right? Because everything past x hat is equal to 0. And the value of the Green's function, well, it's just constant in that domain. It's going to be 1 over the magnitude of a. dy dx hat. So that is going to be 1 over h, 0 to h of x hat divided by a. And that is going to be equal, integrate over dx hat. And that is going to be equal to 1 over h times 1 over 2 h squared a. And what do we obtain? Finally, we obtain h over 2a. So now I encourage you to look back into your notes on stabilized methods when we actually try to choose our parameters. And then we came up with this choice of parameter, or more specifically the choice h over a, as a choice that ended up working very well. So, and back then we motivated that from the perspective of, with when a becomes larger, we want to get, we had an a cross a in there, so we wanted to cancel one of the a's. That was why we divided by a, and then we had a multiplication with h. We had a multiplication with h. Because we said we want our artificial diffusion, is how we motivated it back then, to drop out as we refine. So now we see that we get the exact same expression, but not from hand-wavy arguments, but from very clear set of steps with very clear approximations and very clear definitions. So that is the advective limit, though. So let's talk about the diffusive limit. So that is the case where a is equal to 0, and we obtain as our adjoint differential operator minus kappa times d dx g x x hat is equal to delta x hat. So what does a function like that look like? Well, in our complete domain, and I'll make some larger elements now, so there we go. In our complete domain, again, we have a 0 value all the way outside of our element. This localizes to an element. And we get the exact opposite effect of this smoothing. And what we would end up with when a is 0 is actually two linear functions. So we would get something like this, depending on the location of x hat. This would shift around. So what is the height of this guy? I'll call that d. So the height of d, or the height of this function, aka d, needs to be such that this equation holds. So let's first take a single derivative here. So let me write minus d dx. No, first derivative, sorry, of g. Then we get, well, first of all, a very steep positive value here, and multiplied by minus 1, so we get something like this. And then a less steep negative function multiplied by minus 1, so we get that. And now we know that if we multiply that by kappa and take the derivative, we have to get the Dirac delta distribution, which meant that the jump here, that's going to be the Dirac delta distribution, that has to be, once we multiply by kappa, has to be equal to 1. So this height difference has to be equal to 1 over kappa. So the values that we obtain here are actually d divided by x hat, right? That's the slope of this line. And here we get as a value d divided by h minus x hat. So what we now want is that if we get the jump of this guy, so that is the difference between the end and the beginning, and we multiply that by kappa. I don't know why this is 1 over kappa, forget about that. Then that has to be unit size. So that gives us a definition for the height, d as kappa h minus x hat plus kappa x hat minus 1. And then you can work this out yourself, but this ends up simplifying a little bit, which I just worked out on paper here, but this ends up being I have a tough time believing what I derived here. I think this should be kappa minus 1 times x hat minus 1 over h x hat squared. Okay, so that is going to be my expression for the height of this point. Now, why is that important? Because that I'm going to use that parameter to obtain the averaging of the Green's function. So again, tau d is defined as 1 over h of 0 to h of the integral of our Green's function over y. So for a fixed x hat, we're going to integrate this function. Now, we can work that out in a difficult way or in a simple way. In a difficult way would be that you have to split these functions into pre and post x hat and separate the integral into those segments. The easy way is that we're simply going to use the integral in terms of areas here. So you would get the area of this triangle plus the area of that triangle. So that's going to be half of d times x hat. Plus this triangle is half times d times h minus x hat. Well, then we see that this already cancels, so we get 1 divided by h times 0 h d half times h. Now we have our definition of d. So we get 1 over h 0h, and then divided by kappa, so we get 1 over h divided by kappa. Of, well, we also cancel the h's, right? So then we actually just get 1 over kappa, and we also have 1 over 2, so we have 1 over 2 kappa times x hat minus 1 over h x hat squared. That is going to be equal to 1 over 2 kappa times 1 over 2 h squared minus 1 over 3h h cubed. And we get a pretty nice expression as h squared divided by 12 kappa. And if you look back into our analysis of our stabilization parameter requirements, not what we wanted to have, but what we needed to have for higher order approximations, then you find again that you'll actually get precisely this expression, and this works out actually remarkably well. So you get I don't know to what extent we worked out the required definition, but you get something that should look pretty much exactly like this. So now we somehow have to combine these two approximations into one expression, right? So we have the tau d and tau a as a usable expression for tau, and the thing that we tend to do is we're going to approximate this as what we call an harmonic mean. That's going to be 1 over tau a square plus 1 over tau d square. And that is going to be, if we fill that out in, then we get 4 times the magnitude of a square over h square plus 144 kappa square divided by h to the 4th square root. There we go. So this is our definition of our stabilization parameter, inspired by fine-scale interaction from fine-scale Green's functions that we can also use in a multidimensional case, right? Because this no longer depends on element shapes or difficult functions. No, we can simply use an element length scale here. Based on this derivation, we can now also start to think about what makes sense for our element length scales. I'm not going to go into too much depth there, but you might think of, well, for the advective part, what I want is my element length along the direction of my flow. Whereas for the diffusive length scale, well, I'm really just interested in the largest size of my element, right? So then you can start to play around with these kind of things. So I suppose only this approximation kind of drops out of nowhere. Let me show you though that this actually works quite well. This is a set of graphs that you would obtain if you perform that approximation, where the green line is the true definition of tau, following this very difficult expression. So you can work this out as well. You can work all these integrals out. You would get the green line for P1, and the red dotted line is if we make use of this approximation. So we have these limiting values, limiting cases, and you would substitute those in here. Then you would obtain the red dotted line. And this is for a range of different Peckley numbers. Peckley numbers mean a different ratio of advection and diffusion. So we see that that works out really, really well, surprisingly well for a whole range of advection and diffusion. Yeah? So there's no need of working out this complex expression for your implementation. You can simply take the limiting values and get a very, very good approximation of the whole range of values. Now there's two more lines in here, P2 and P3. You can work this all out also for more complex fine-scale Green's functions, right? We saw the ones for quadratic and cubic basis functions. The expressions become more complex, but it ends up working the same way in principle. And also the approximation is still very effective. Okay, so then to summarize all of this into one equation, our fine-scale interaction, Bu prime VH, is going to be approximated by a sum over elements of our residual of the core scales minus times our tau approximation times the adjoint operator acting on VH. Yeah, this is a stabilized finite element method inspired from a fine-scale interaction with very clear definitions of stabilization parameters from fine-scale Green's functions. Okay, that's it for this one. In the next one, we're going to talk about how you would actually get now an SUPG or a GLS formulation rather than this adjoint operator in here. Okay, see you in that video.